Hello class, this is Dr. Ben, and let's work through one last problem on the topic of projectile motion that is the last part of Chapter 4. So this is a classic scenario about Galileo dropping the rocks off of the Leaning Tower, but instead of dropping the rocks, this problem has Galileo throwing the rock or rocks at people that are down below. And so rather than being just a vertical motion problem, this is a problem in projectile motion. So Galileo is up in the tower, and there is a spot that we're supposed to focus on where the rocks land down below that's 15 meters from the base of the building. So let's draw a pictorial representation of this situation. So we'll do that on an ordinary XY coordinate system, and we'll have Galileo at the top of the Leaning Tower throwing the rock, and then it is going to follow part of a parabolic path until it hits the bottom, the ground, and we'll label this as point 1 and this as point number 2. And we should indicate that the direction of the initial velocity, which would be v1 in this case, makes some angle below the horizontal, and that's given in the problem. Alright, so rather than putting all of the kinematic variables on this diagram, we'll just write what we need in our tables, but we should indicate the direction of the acceleration just to remind us that a sub y is going to be minus g in this coordinate system. Alright, so we don't know how high Galileo is off the ground. We don't know that. We do know that the angle is 30 degrees, and I'm going to indicate that that's below the horizontal, because that will help us get the direction of the y velocity. We need to know whether that angle is above or below the horizontal. Alright, the rock takes 3 seconds to hit the ground in 15 meters from the base. So the initial position, x1, we can set to be equal to 0, and then the final position, x2, would be the 15 meters. And even though we don't know the value of y1, we do know the value of y2, that would be on the ground. And we can set t1 equal to be 0, and we're given that the value of t2 is 3 seconds, and g will use the approximate value of 10 meters per second squared. Alright, so what is it we want to find about this rock? So back to the problem, we're told to calculate that speed, which is the speed at which the rock hits the ground with. So the director is worried that somebody might get hurt, essentially. So we would like to find not the vector, but only the magnitude of the velocity at point number 2. Alright, so what my strategy is to find this speed by using Pythagorean's theorem and using the velocity components. So v2 would be equal to the square root of v2x squared plus v2y squared. And so now we can start to use our physics concepts to work our way through this. So in the x direction, we know that projectile motion is one in which there is uniform motion. Essentially, that's the definition of projectile motion. And so that implies that the horizontal velocity does not change. So the velocity in the x direction at point number 2 is going to be equal to the velocity in the x direction at point number 1. And we can easily get that by using our vector components, because we can see that the vector, the velocity v1, has a negative y component in the coordinate system that we picked, so it would be equal to negative v1 times the cosine. I'll try that down below. Negative v1 cosine of theta. So that's going to be v2x. And even though we can't come up with that number yet because we don't know the value of v1, we weren't given that, we've got that at our disposal when we're ready to use it. Alright, so that's the x part of the motion. Projectile motion has uniform motion in the x direction. So now we can start to consider the y motion, which is accelerated. So in the y direction, because we don't know anything about the height of the tower, the only equation in the y direction that is really useful is the one that relates the velocities and the acceleration and the time. And so that would tell us that v2x would equal v1x plus, oops, these are in the y direction, sorry about that. All right, we'll try that again. v2y equals v1y plus the acceleration in the y direction times t2 minus t1. All right, so we'll work with that a little bit. So v2y is what we want to find. v1y would be equal to v1 times the sine of theta, but that should have a minus sign in front of it because that initial velocity is downward, which shows me that I made a mistake on the previous part. That x velocity should have been positive and not negative. It points to the right. This was the one that's negative. So the v1y, we can go back to our picture real quick and see its y component is negative in the coordinate system that we picked. All right, and then the second term plus ay will be equal to minus g times t2 minus t1. That'll just be the value of t2. So that's what v2y equals. And I will just put a box around that equation at the moment because I can't really do anything with it because I don't know the value. Oh, I do know the value of t2, but I haven't found out the value of v1 yet. So just like with the x direction, we still need to find the initial speed of the rock that Galileo throws before we can find any of these final ones. All right, so back to the x motion again. Because in the x direction, we know the displacement, and we know the time, and we know that the x motion is uniform, so there's no acceleration. So therefore, we can write down that the first kinematic equation, x2 equals x1 plus v1x multiplied by the time interval t2 minus t1. There isn't a third term because there's no acceleration in the x direction. And in our problem, we have the value of x2. That is equal to 15 meters. The value of x1 is 0. The value of v1x will be equal to v1 times the cosine of 30 degrees. And the value of t2 is the 3 seconds that we're given. So we actually have enough information here to find the value of v1. So if we cross multiply, v1 is going to be equal to 15 divided by the cosine of 30 divided by the 3 seconds. And so we can figure that out on our calculator, and that will be 15 divided by the cosine of 30 divided by 3 seconds, and that equals 5.77 meters per second. Let's check that one last time. 15 divided by 30 cosine divided by 3 seconds. 5.77. Okay, so that helps us a lot because now we can use that to find the value of the initial velocity in the x direction, the final velocity in the x direction, and then we can also use it to find the final velocity in the y direction, and then finally we can use Pythagorean's theorem to put all these pieces together again. So let's try to be systematic about it. So v2x will be equal to v2 times the cosine of theta. Then we can come up with that number, so that will be our 5.77 times the cosine of 30 degrees. So that equals 5.0 meters per second. Then, from our equation up above, now that we have the initial velocity, we can find v2y. So that will be equal to negative 5.77 times the sine of 30 degrees minus 10 times our 3 seconds. And so we have 5.77 times the cosine of 30 minus 30 gives us negative 5.77 times the sine of 30 minus 30 equals negative 32.9. Negative 32.9 meters per second, and that points down, which is consistent with our coordinate system. And then finally, we can put those two together by using Pythagorean's theorem to find out what v2 is. So that would be equal to the square root of v2x squared plus v2y squared. So we'd have the square root of 5.0 squared plus negative 32.9 squared and that gives us 33.3 meters per second. All right, and so that is pretty fast, and it's on the order of 60 miles per hour. It's not exactly 60, but it's close enough. So the director's concern about rock chips flying after this rock hits the ground are probably well-founded, because this rock was leaving Galileo's hand at 5.77 meters per second, which was around 12 miles an hour if we double it. But by the time it hit the ground 15 meters away, it's going around 60 miles per hour. All right, so we'll finish up. We'll make sure we have our units and our significant figures, and I think we have this problem done.